Good afternoon. We start our afternoon session. It will consist of presentation from different other codes. Let's say the arrow code, which is one of the most used code in fusion and magnetic confinement fusion community for simulating of impurity. And Samuel Lukash, brave student, he will present this. He's a aero specialist here. Then we will have presentation from Daniel Swartz. He will present IRENE code. So IRENE is a neutral trace code, also very commonly used in fusion and not only fusion community. Then we have discussion from Aleš Podolnik, who represents the SPICE 2 and 3 code community. And then at the end, we will discuss some adjustment vectorization attempts for the BIT1 presented by Kalia later. So Samuel, please. Thank you.
Okay, thank you, David, for this introduction. I hope that everyone also outside can hear me well. And I will just, maybe I will repeat that this presentation will be dedicated to the Aero 2.0 code, which is a code for impurity modeling, as David said, mostly for magnetic fusion devices, but not only for that. So the presentation is supposed to be somehow related to Monte Carlo method so that you can compare with the BIT1 code. But definitely I will also show some overview of the code, some basics, some basic input and output for the case you manage in your career to meet someone working with this code or you manage to somehow work with the data yourselves or the outputs. And then of course some works regarding the most ones, let's say, and my work and some conclusion, of course. So the code, yeah, they are still coming, a few people. Okay, good. So you are not everyone here is familiar with the fusion devices like tokamak is. So I will just briefly present it because most of the figures are shown from the tokamak environment. So here on the middle figure, you can see the basic view inside the tokamak, which is a machine or device used to confine plasma. So basically, the plasma is confined in most of the volume, which you cannot actually see. You can only see the interaction with the wall of the vessel, with the plasma-facing components. And so here, basically, in those toroidal circles, that's where most of the interaction happens. And so, to put it in the point in the point of view of the code, basically here is where we start our journey. These are the fluxes of plasma which comes into contact with the material. Then the code basically simulates via the sputtering yields, the physical erosion, chemical erosion, or anything else if you manage to get some data for it. So after the particles or the impurities from the wall, from the material are released, they can of course be ionized. Then the basic tracking happens. As the particles are magnetized, they are following the magnetic field lines towards the main plasma, where they can cause troubles for fusion. They can dilute the plasma. They can cause the power loss from the plasma. So therefore, it's very important to use such a codes to really track those impurities inside the plasma, and also to track where they are then deposited over the vessel. So the code itself during the tracking part, it assumes most of the basic plasma physics like friction, thermal force, of course the Lorentz force, and there are some approaches how to handle the diffusion, which is very specific, let's say, in fusion devices. It is also important to say that the code assumes the test particle approximation, which is kind of different to BIT1 or maybe generally particle in cell codes. That means that basically you always have to assume that the particles which you simulate do not affect the plasma background which you provide to the code, which is, let's say, not true in any case, but somehow at least it is reasonable. And then of course the particle can be deposited, reflected, or whatever. Regarding it's a massive parallel code. not as much as the BIT1 code, but still it uses the, I would say, basic hybrid NPI OpenMP scheme. I do not know much about it, so you don't need to ask me much about this topic. And it's written in C++. You can see that the simulation time of a basic run takes like up to 10 to the 5 CPU hours. But I mean, you can simulate basically on a supercomputer in like an hour. You simulate the whole tokamak, the whole chamber, with some reasonable amount of particles. Then to some basic inputs. So basically you need the whole plasma background, you need the magnetic equilibrium if you are interested in devices using some magnetic equilibrium. The plasma background is usually obtained via some fluid codes like slow PS ITER, in case you heard of it, or SOLEDGE or UH. These are all tokamak related codes, or magnetic confinement related codes, let's say. So basically you provide the temperatures, densities, parallel velocity, but also you can provide the electric fields, conductive heat fluxes, which are then transformed into the thermal force, density, temperature of neutrals, and then additional transport coefficients if you need them. I will talk about them later. But then, of course, some atomic data, which here it is mostly handled in the most easy way, which is from the ADAS library. Therefore, you will get the ionization recombination, the effective rates, the emission coefficients for the emission, and then for the reflection and sputtering yields, some trim codes or experiments if you manage to find it. But let's say the Aero 2.0 code is a new one. It's been released a few years ago, and before it, there's been a large history of Aero, now called Aero 1.0, let's say. And there has been a large library of molecular data already there, so it's kind of becoming famous only because of this library. And then, of course, you need some mesh. It can be 2D, it can be fully 3D, which is really why the Aero 2.0 is so popular, because it can simulate the whole 3D machine. And what is some basic output? That would be like these 2D, 3D density distributions throughout your vacuum chamber, throughout your vessel. You can then immediately recalculate it to the emission if you have the emission coefficients, and then compare with the experiment. So you can see here on a case of JET, which is one of those larger tokamaks, that it can match really quite well the data. Or if you are focused more about the plasma-Bohr interaction, then we have here, then we can get like those toroidal cutouts or the whole toroidal chamber, but usually it's toroidally symmetric in some sense, where you just get the values for the erosion, the net gross erosion fluxes, the deposition, of course. Or you can also simulate some recessed areas. Here it is not really visible, but you can imagine that the whole tokamak vessel would be like around here, let's say. And here is just some small window for some diagnostic mirror where you can simulate over time how much of the impurities will be deposited on the mirror and how it will be damaged by that. Yeah, and now to some numerical physics. So here, just so that you can somehow relate to the bit code, I can imagine, because we use, I guess, I at least hope so, that we use the same scheme, the Boris method, to solve the leapfrog scheme. So I hope that you are all familiar with that. But also, again, recently there has been added this guiding center approximation, which is, of course, a much faster way how to track the particles if you track only the particle via its gyro center and then according drifts. But of course, you need to keep in mind that it doesn't work everywhere, because there's the limit for the gyro rotation. And this scheme is then discretized via some Runge-Kutta schemes. But throughout my presentation, I will focus on other slides only to this case, because the physics is written in a simpler way, so just easier for you to understand. But otherwise, all the physics should be also available for this scenario, let's say. So first, the collisions with plasma. Here it is treated that you always have the plasma background from some, let's say, mostly from the fluid code. So you assume that it's Maxwell-Boltzmann distribution anyway. So basically, you just need how the particle interacts with the Maxwell-Boltzmann distributed background. So that's much easier compared to the BIT1 code. And here it is only assuming additionally this gradient, temperature gradient correction for the Maxwell-Boltzmann distribution, which then gives you immediately also the coefficient for the thermal force. So that's why is there this contribution. But otherwise, you have from the let's say classical analysis, the classical diffusion and the friction term, which you then add all together to the velocity before you calculate the Lorentz force pusher for each particle. How the collisions with neutrals is handled? That's basically again the easiest way possible, I would say. Because we, for most of the cases, not for the case when we track really the hydrogen or the fuel isotopes, I mean deuterium and tritium, we assume usually the Hartz-Fierce model, which is defined, which just defined cross-section via the van der Waals radius. So then you can very easily calculate just the collision rate, the probability of the collision, and this probability collision you then just compare with some pseudo-random number, and that just basically decides whether the collision happened or not, and you can immediately another contribution to the velocity to your particle. Then there's the thing in tokamak plasmas about the anomalous transport, which is just increased transport, which we do not know where it comes from. So I do not know how it is really handled in other plasma devices, but definitely you could assume some additional transport anywhere. So if you want to do that, there are just some basic two coefficients for the convection and diffusion for the transport equation. So basically, you just add them into the scheme like that you change immediately the position, not really changing the velocity. So that's kind of interesting how really the energy or how really the scheme for the tracking really works. That it's kind of you will basically. I will not talk about it now. I will just move on. Maybe at the end. So let's move on to the atomic processes. So again, just a very simple approach. If you have the effective coefficients from the ADAS database, then you have immediately the ionization recombination times, which you put again in the exponential form for the probability. So it works very similar to the collisions with neutrals. And then just compare it with random number, and you have it. The emission is because we assume the how is it called? Sorry, I need to remind myself. Dest particle approximation. Then the emission you can calculate only at the end. So that's very easy because you basically do just one calculation at the end from the density distribution via those photon emission coefficients, again from ADAS usually. But let's say now the more interesting part, how the plasma sheaf is handled, because in BIT1 you calculate it self-consistently. So in Aero, we need to assume it again just as a plasma background. So usually, or the easiest way how to do it is to use some analytical formulas. Now there's the default version of Irina Borodkina, which is now also one of our colleagues here, now on maternity leave. Where the sheaf is prescribed analytically, so that's very simple way how to do it. But there has been in history also there has been some approaches how to couple with some PIC codes the collisional sheaf to Aero, or in history it was maybe for just standard sheaf, I don't know actually. But nowadays it is important for high density devices like the compass upgrade will be, or the first fusion power plant is planned to be, that there will be the collisional sheaf needed. So there's definitely also some interest in the BIT1 results. Then also last thing regarding the tracking, that's also the neutrals, how they are tracked, because you already very well knew that if you sputter a particle, it's usually released as neutral, not really as an ion. So basically the neutrals are handled in a similar way regarding the collision with other neutrals. But there's also, in addition to that, there's also friction of neutrals with ions, which is something I would say special, because that's not really common in other codes, I would say. So now we are really talking about the friction of neutrals with ions, not really ions with neutrals. Yeah, so it's the other way around now. But it's this is the cross section for that is also known for many years. You can see it from 1966. But this has just recently been added because of measurements on one of the linear plasma devices, Magnum PSI, where they seen too high prompt redeposition values for the erosion. So they thought that this force might be important. And it's added again in a very simple way and added to the velocity. So now, just about the works, I will first allow myself to talk a little bit about my work, what I do with the code. So I've been trying, or I started to work with the code on validating the liquid metal experiments with the code, or validating the my simulations with the experiments. Sorry, and that's been done on a former compass tokamak, which is no longer here. But there, the experiment basically consisted of inserting this liquid metal prototype tile, which is basically a mesh soaked with some liquid metal that's been inserted here at one position in the tokamak. And it's supposed to be like a new plasma facing component, very, very, very robust, but I will not go deeply into that. But you can see that the released liquid metals, in this case lithium, been emitting, of course, light in its ionization states or charge states. And this pattern can be simulated, so you can see some comparison. It was not really finished up till now, so I'm still working on it. But then I decided to move on for the predictions for the new compass upgrade tokamak that's just being built right now. And here we did some more serious approach, but let's say it's still not finished. So I will just rather move on. And I'm not simulating only the liquid metals, I'm also simulating tungsten. So you can again see those like nice density distributions, even though this is not a finished simulation, but I've been at least trying to simulate the effect of the electric field or the thermal force, which you can see here from the source, like somewhere at the bottom of the chamber. So how the concentration in the core changes according to the implemented physics. But to some maybe more interesting works, I have chosen just one, just for the ITER tokamak, which is or will be the most famous tokamak after it's finished, even though I would say it's the most famous even now. It's in France. It's supposed to first reach the positive or positive net value, net energy value from the fusion. And so there has been many studies dedicated to that. You can see here, just for example, the one of the toroidal cutouts. So that's basically what you can do with arrow. Just simulate the net erosion from the walls, and then you can see the critical areas. But here there has been also studied the effect of impurities, as you can see that from the percentage of neon, which is a gas that can be puffed into tokamak for various purposes, or let's say for just one, but I will not talk about it. As you can see that if the impurity increases from 0 to 1% in the plasma, the tungsten flux, of course, can increase like orders of magnitude. So that's bad for the fusion. So it needs to be studied. And just another example. So you can again just see that the erosion of beryllium, on this case on the left, and again the tungsten has been studied in like those nice maps and poloidal or 2D cutouts. So that's basically what you can do with the code, how the results look. But there has been many works around the whole world, and not only dedicated to those easy or to those simple outputs, but also you can study with that code the surface morphology evolution, as you can see here on the figure on the right. How it then affects the total, let's say, erosion yield from some like representing flat surface, representing this area. Now to the conclusion. So I just showed you what the Aero 2.0 code is. It is a parallelizable 3D Monte Carlo kinetic code used for erosion and impurity transport in plasma. It is optimized for fusion devices. Basically, the Monte Carlo, as I tried to present in those few slides, is implemented, I would say, in the simplest way possible. That each particle, each step decides whether something will happen, which is different to BIT1, where you first calculate how many collisions happened, and then you randomly select the particles as David just presented, or if I got it correctly. And then there's the opportunity for people that they are important for this code to give proper sheaf parameters. And I'm working for simulations for the compass upgrade tokamak, mostly, or for the liquid metal and tungsten heat shields, erosion, and transport of subsequent impurities. So thank you for your attention, and I'm ready for any questions.
Thank you, Samuel, for nice presentation and your agreement to present us, code. I have a number of questions. First of all, can you remind me, so when you go to Monte Carlo part, the principle, so it's kind of direct simulation Monte Carlo, yeah? So it means that you calculate for each particle the time for collision, and you are counting then until this collision comes.
And not exactly. It is kind of the other way around. You basically have a fixed time step. At least I will now talk about just the classical collisions with the background plasma. Yeah. So you have a let's say just for simplicity, you have a constant time step. This time step, each time step you check whether you have the collisional time step is higher or lower. So then you basically divide this time step according to the collisional time step. And for this collisional time step, you calculate the number of collisions it results from that. But you do not do it the way that you would really keep the time between collisions. You basically, each time step, you check how many collisions you did. Yeah, so it's kind of the other way around, let's say.
So you just check how many collisions you did, and you know how many had to happen.
Yeah.
And then if it's missing, then you are doing given number of collisions.
Yeah, like that, yeah.
Okay. Okay. And what is the difference between the tungsten collisions, which said, and usual neutral particle collisions? So you said that it's a
you mean
for
this one?
prompt reposition, you say.
Yeah, here. This is because this is regarding just the neutrals, when you track only the neutrals at the beginning. Yeah. So here's the additional friction force with ions. So it's not the usual friction force where the ions are dragged by the background plasma. This is really for neutrals, which can be also
kind of
affected by that.
hard sphere approximation, kind of.
Yeah.
Okay. Yeah. And if there are no other people asking with questions, let me ask the last question. This, I don't understand the sheath model. If you go to the sheath model, yeah, I mean, according to, I don't understand the last expression for the magnetic pre-sheath. So if theta B, which is angle, as I understand, between the normal and the magnetic field, normal to the wall and magnetic field, yeah, this is so.
I actually do not know what actually the theta means here, but.
But I mean, if you go to LMPS, or magnetic pre-sheath length, it's some number K multiplied by the I and J radius, otherwise sinus theta. So if theta is 0, this is 0. It means that theta 0 means it's normal to the. So you have no magnetic pre-sheathment. Magnetic fields normal to the wall. But now if I go to potential drop, so this I don't understand, because if you have
actually
0 on 90 degrees, this parameter goes somewhere else. So if it's 0, so we have 1 and we have 0. Yeah, but now if you put now you are, let's say, near 90 degrees. So if you assume that it's 99, so ln of, so it's a 0, 1. So it's quite, so it's a less than 1.
I think they are not actually from Stangebe. I copied them.
I'm not sure, yeah.
I haven't seen them in Stangebe. Maybe they are there somewhere.
There could be mistake in Stangebe books. So I mean, no, I mean, this is another point. This is because, I mean, if it's 1 degree, yeah, you get minus, I don't know, 10 times temperature drop, yeah.
But to be honest, I did not even check whether these formulas are actually what is implemented in the code.
I think something else is sitting there. It should be 1 minus or something like this, yeah. That's true. That's true. For 3 degrees, there is no Debye sheath. But I mean, okay, maybe, yeah, but
maybe it's an approximation with a total drop that is constant, which is not correct, of course, across magnetic pre-sheath and the bi-sheath, maybe, but.
So it seems to me that phi W comes from a fluid approximation of the magnetic sheath, which is the sum of the potential drop across the magnetic pre-sheath, so like the magnetized part, in which is quasi-neutral, and the bi-sheath. And this is more or less independent of the instance angle, because essentially, if you take a very simple fluid model, whatever potential drop that doesn't happen across the Kadura or the magnetic sheath happens in the bi-sheath. So essentially, if your theta b is 0, which would indicate normal instance angle, so you have no magnetic pre-sheath, all of the potential drop will be taken by the bi-sheath. And usually this around like minus 2.5 volts, which is exactly what's indicated in this graph here. And if you're at very shallow angles, so theta close to 90 degrees, then the Kadura sheath dominates, and you will have this phi MPS, which is very large, and the bi-sheath is basically non-existent, as David pointed out.
Yeah, in fact, when you do this approximation, the formula gets wrong when you have a very small angle with respect to the surface.
Correct. Yeah.
That's what David was pointing out. I think it's normal because of the approximation.
No, let's shift this discussion, because I mean, I partially agree, but this is because I was working with Stengme about this, and it's not this expression, but anyway. So we are speaking about error. We have to be very careful. I really suggest to check this, because first of all, check, which Alex mentioned, at 3 degrees there is no plasma Debye sheath. But anyway, so this is I mean, not the important point, just my suggestion to check what is, and we can do it because this coupling was done with BIT1, and we show quite different results, but this is just a separate thing. So anyway, thank you. It's really good work, and I really looking forward for really full simulation of the error for Compass Upgrade, because Compass Upgrade is one of the most difficult machines to simulate, and yeah, so let's see what comes out. Thank you very much. Yeah.
Thank you.
So I would just have a short question on the, you had written in the anomalous diffusion, how is the V for anomalous, what is it based on, this V
This one?
anomalous? Yeah.
Well, that's the thing that you can put there basically anything. But
Yes,
if you would relate
I know,
it
but
to,
what do you base it on?
if you talk about just tokamak physics, let's say,
Yeah.
it is one of the unknowns that you
Yes.
can maybe simulate with, or at least somehow try to simulate with the fluid turbulent codes.
Yes.
Yeah, but usually it's just some experimental assumption.
Okay, so I mean, like I asked, so what do you take?
Sorry?
What do you take? What number do you take?
Okay. Well, if I simulate, because I try to show you that I simulate liquid metals, which can be lithium or tin.
Yeah.
So for tin, this I actually do not need to assume the anomalous transport. I can assume, let's say we call it neoclassical transport coefficients. And these are well known. So these are from somehow analytical models, which are quite correct with the experiments. But in the case of low Z impurities like the lithium, I usually take ones that, in the case for compass upgrade, we have also some, let's say, predictive capabilities on those anomalous coefficients from the METIS model, which is for the background plasma. So I usually, for the low Z impurities, I assume the same coefficients as for the background plasma. Yeah.
Okay. So for D, I think you probably take like 1 meter per second square or
something like that. Yeah.
Okay, thank you.
Yeah.
I had the last quick question. I just wanted to know what kind of resolution you impose in your simulations. So you mentioned you use meshing. Can you use adaptive gridding or?
I've been also warned by my colleagues from Jülich, where are the aero developers, and they told me that I should be somehow more specific about what I mean by the mesh. And by this, I do not mean the mesh of the background plasma, which is completely different thing. I mean just the mesh of the surface plasma facing components. Yeah. So for that, I do not need actually any mesh refinement during each time step. This is just the mesh to somehow on which you can converge with your deposition, let's say. So if you want to have more resoluted patterns at the end of the simulation, you just decrease the simulation of the mesh here. Yeah. So I hope this is where your question was going, or if not, then correct me.
Typically, what is the you mentioned you kind of try to resolve at least the plasma sheath to some extent. But then you also need the appropriate meshing to go with it. I assume you're not resolving the bi-sheath everywhere.
Then we always assume that the sheath is like taken just in like radial direction. Normal direction from the surface. So let's say the mesh of the surface doesn't actually affect the sheath anyhow. Yeah. And then the sheath itself in the normal direction is actually not resoluted at all. It's assumed only analytically. So basically, you know the position of the particle, how far it is from the surface, and therefore you can just immediately calculate for this one particle what is the.
Okay.
Yeah.
Okay, I see.
Yeah.
Cool. Thanks.
Yeah.
Thanks once more.
Thank you.
And now invite second presenter, Daniel. Please. Daniel, as I announced, is working with SOLP's ETA code. It's a fluid code. Which one? So PPT or?
Doesn't matter. I use both.
And the part of this SOLP's ETA code is IRENE. IRENE is a Monte Carlo code which simulates neutrals. And now Daniel will speak about this case. Yeah, thank you. Just to let me. Oh, I didn't share it. Sorry. Let me share first. Okay.
Okay, so my name is Daniel Schwartz, and I'll be presenting the IRENE code, which is a Monte Carlo code for neutrals transport, so neutral atoms or molecules. I'm not an expert on Monte Carlo or IRENE by any means, so take this just as some general overview of the code and its capabilities, and maybe some interest to you. So just an introduction, as I said, IRENE is a Monte Carlo solver for neutral atoms, deuterium atoms or molecules or impurities. In general, it's a multi-purpose Boltzmann equation solver. So it solves it solves the transport of the neutrals on a static background plasma that's used as an input, so usually from fluid codes. It was inspired originally by neutron transport codes, so like in fission reactors. So it traces individual particles, test particles, through the computational domain, and then statistically analyzes and tracks various quantities of interest. It's heavily employed by the fusion community. It was developed to understand various processes in tokamaks or fusion experiments. For example, to understand detachment in the diverter region, or to understand fuel and impurity transport throughout the scraper flare and potentially into the core. As it is typically used iteratively with plasma fluid codes, as David mentioned, SolPS ITER, which is a combination of fluid code BIT1, which handles the plasma, of course, and IRENE, which handles the neutrals. But there are also other codes like EMC3, which is a Monte Carlo fluid code in 3D, or H2D, and others. And it was developed at ULIC. So just some motivation about why we even care about neutrals at all. So in a tokamak or some fusion experiment, the plasma leaves, or the ions leave the confined region. They travel through the scraper flare quickly along magnetic field lines, and they impact the wall or the diverter, where they are neutralized. So of course, they are no longer affected by electromagnetic forces, and then they travel using randomly back through the plasma or through the chamber to the plasma, where they get ionized again. So these two processes of the plasma transport basically outwards, and the neutrals coming back and ionizing in the scraper flare or in the core back, this balance determines the density and temperature in the scraper flare or in the edge. So properly simulating and analyzing both of these processes is very important to get the self-consistent solution of the edge plasma region. Also, this neutrals transport is of interest because of fueling efficiency of the core. It's important to know where these neutrals get ionized, because if they get ionized in the core, they contribute to the fueling of the core. But if they get ionized in the scraper flare, they don't even reach the core. The core starts losing particles, basically. And of course, so in a previous presentation, transport of impurities is important. So IRENE can help at least with the neutral part of that. Yes, so just some general mathematical background of what equations are solved, or what is the Monte Carlo doing. So we, of course, try to solve for the distribution function, which is like a probability of finding the particle at some position in a phase space at position r and velocity v, time t, and species index I, or it can be written with energy or and unit vector direction. The equation that governs the transport or time evolution is the Boltzmann equation, which is written here for finite range interaction potentials and elastic collisions with neutral distribution Fi0 for some species I0 on a fixed external background Fb of the plasmas. So in this case, the collision term on the right can be separated into two integrals and source term Q. The first term, the first integral describes the total rate of collisions into the velocity space interval. The second term describes the loss from that interval, and it can be the second term can be integrated using some energy and momentum conservation laws, and we can get different form, a linearized Boltzmann equation, which is linear, so it only shows a distribution of the neutrals that we are trying to solve for. The loss term is now represented using a macroscopic cross-section, which is basically an inverse mean-free path. And the gain term is represented using some complicated collision kernel C, which has all the collisions that can happen with the interactions of the neutrals with the plasma, including particle multiplication and things like that. Usually we only care about a time-independent solution, so we don't have to count this term, and also neutrals are not really affected by external forces except maybe for gravity, which can be neglected, except for collisions, of course. So finally, we can rewrite this Boltzmann equation into much neater integral form for some collision density, but it doesn't matter. But what's interesting about this equation is that it resembles a general equation for a Markov process, where we have some source of primary birth point of particles into a position, a state X, and some integral which describes the probability or transition from all the other states into this state X based on the probabilities in the transition kernel, which depends, of course, on the transport and again on the collisions, which are very difficult to compute numerically or in a standard way. But with this form, it's easy to see that it's well suited for a simulation with the Monte Carlo method, with this form of Markov process. So that's nice, but I think it can be much more intuitive to think of it in a physics point of view, because this particle transport is microscopically made up from transport of many different particles. So the particle transport is a stochastic process, and a direct simulation of the transport can or should be also a stochastic process. And this is exactly what IRENE does. It traces many different test particles through the computational domain, and then it statistically determines the quantities that we want to measure. There are several assumptions that makes this model easier. Particles travel only in straight lines without losing energy between collision points. Particles suffer a collision per unit distance with some probability sigma t, which depend on the rate coefficients or cross sections. Time duration of the collisions can be neglected, and the particle transport is linear. How does a single test particle how is it traced? It first is sampled through some source distribution function based on the source, so through recycling or volumetric recombination or gas path or other source to get the initial condition or state, basically. Then the mean free path is calculated based on the energy of the particle and basically the background and the rate coefficients or cross sections. This mean free path is then sampled to get the actual distance traveled. Then the collision type is sampled, and the state is calculated based on the type of collision. So for elastic collisions or maybe charge-charge exchange, we can simply exchange the neutral particle with some background ion and other types of collisions. And then we also have to keep track of which events are happening during this tracing to tally or record this information to get the quantities that we want. And we repeat this step until the particle is ionized or it's lost somewhere. So by simulating many different trajectories or particles, we can get some statistical analysis approximation of some values that we want. This is an example of one such particle of a helium atom and its trajectory in a stellarator, where it gets born in this green point, and then it travels through the stellarator and it gets ionized in the plasma. IRENE uses external databases to get the cross sections for the atomic and molecular processes. Mostly, it uses Maxwellian averaged rate coefficients because it's usually coupled with fluid codes. There are several databases that were made specifically for IRENE, right here. As well, it uses other external databases such as ADAS. So what happens to the particles when they encounter a boundary? They can undergo different reflections or reactions for particle reflection or thermal particle emission or absorption, which these probabilities and the resulting energy of the particles depend on the incident energy and angle and the species of the particle. IRENE uses two models for surface reflection: the Barish matrix reflection model, or in addition, a database of trim code simulations. As IRENE is usually coupled with fluid codes, it uses the ion flux that comes from the fluid codes to get the source of neutrons coming from the diverter. But fluid codes don't really simulate the sheet physics, so it uses some simplified models for the electrostatic sheath and magnetic pre-sheath. Sorry, I don't have the equations here. Also, a recycling coefficient can be specified to model or simulate maybe bumping surfaces in the experiment. And also neutrons that maybe reach deep into the confined region, into the core, can be thought of as being ionized, and it's because of the increasing density and temperature inside the core, so it's not necessary to simulate them. So, of course, we want to get some information from the simulations. So IRENE uses two types of tallies or unbiased estimators to get estimates of various quantities. It uses collision estimators, which basically track the number of collisions inside some region or a cell. But because collisions can be quite rare, especially in some regions, it might be beneficial to use track length estimators, which calculate the distance the neutral particles travel inside the cells, which is then summed together to get a different type of estimator. And one advantage of this Monte Carlo method or these estimators is that they are unbiased. So the mean value approaches or is the same as the true mean value of the physical process. So they are not affected by mesh discretization, where maybe other codes can get a different value based on the mesh discretization. So in IRENE, variance, because there is of course statistical noise from the Monte Carlo, variance can be reduced simply by increasing the number of test particles. IRENE supports two types of geometry representation. First, boundary representations, where surfaces and volumes are created using different Bezier functions or B-splines, but usually with coupling with fluid codes, voxel geometry is used because that's what the fluid codes use. So IRENE uses triangles or quadrangles, for example, in 2D in coupling with the fluid codes. On the right, you can see an example of compass upgrade for a SolPS mesh, where, well, it's a mesh for both the IRENE and the fluid code B2, where the cells are aligned to the magnetic flux surfaces, which IRENE doesn't really need, but the fluid code does. So in this way, they can transfer the quantities between the fluid code and IRENE. So about coupling with other codes, as I said, it's usually coupled with fluid codes, where both types of codes need each other's data to get some self-consistent solution for the edge region. The plasma codes provide background density and temperature and fluxes to the surfaces. IRENE then takes these as the background input of the plasma, traces the particles based on that, and provides the ionization source or the source terms for the fluid equations for the fluid code, which is then repeated iteratively until hopefully some convergence is found and residuals fall below a certain threshold. Some examples of coupled codes. We already mentioned SolPS ether, which is a combination of B2 fluid code in this blue mesh, and of course IRENE in this triangular mesh. And also EMC3 IRENE, which is a 3D Monte Carlo fluid code. So it can it's often used for stellarators or some investigation of some toroidal effects in tokamaks. Yeah, there are some features I didn't really talk about that IRENE has. For example, a time-dependent mode in cases where a steady state solution is not sufficient, for example, in tokamaks with ELMs or some short duration processes. So IRENE can do also a time dependent or time evolution of the neutros, which is pretty simple with Monte Carlo, just by adding another dimension with some small time increments. But of course, we also have to tally the information of the time of flight, basically, or time to collision, to get the time evolution of the particles. IRENE also is extended for photon transport, which is in some ways similar to neutros transport. So it can simulate test photons that incorporate the different processes like Doppler broadening or stimulated emission and other processes to get estimates for different diagnostics, like line of sight diagnostics, or better investigate the effects of power losses or radiation in dense diverters in detachment in tokamaks. Okay, that's so. As a summary, IRENE is a Monte Carlo solver for neutros transport and their interaction with plasmas. It uses random sampling of collisions and emission absorption events to solve basically the Boltzmann equation. It is used often in it's typically used in conjunction with plasma fluid codes like SolPS ether, where they iteratively converge until some self-consistent solution for the scrape-off layer. I think that's all. Thank you for your attention.
Thank you, Daniel. Questions? Please. There's a question from Michael, please.
Yeah, thank you very much for this wonderful talk. I have actually two questions. The first one is you already mentioned the coupled self-consistent simulations. So what is the interface here? Is it because it seems that you're coupling more than one code to IRENE? So is there a standardized interface for this?
Yes, there is a general interface for fluid codes, basically.
Okay, wonderful. And the follow-up question to this is we have now seen with this session several codes that require atomic physics data. Is there a coherent approach towards collecting and providing this atomic physics data? So in form of a common data description, common data format, and so on by now?
Let me answer this question. I mean,
okay.
No, there is no very short answer. There was attempt to generate under EFTA that time, so it was predecessor of Eurofusion, to have a separate description, which is still called AMNS, atomic molecular surface and nuclear data, which is now part of the IMAS database. IMAS is a ETA database, but it's quite poor for cross sections. So as I was mentioning during my presentation, the data providers, because of historical reasons, we are mainly concentrating on the rate coefficient. So Aero, IRENE, DIVGAS, and many codes are using, which are coupled with neutral, with fluid plasma codes. They need interaction with fluid plasma, assuming that fluid plasma particles are Maxwell distributed. Otherwise, you cannot apply fluid approach. So they need rate coefficient. So requirement is more or less common. For instance, there is a ADAS data. It's a UK provider, of very good provider, and one of the main one. For instance, there is a Lukas helped me. This is a data from the IRENE, and I think it's used also separate data from others. It's also used by both codes, but these are once more rate coefficients. So if you want to have standalone approach, then you need cross sections, and you have to search for the data separately, like we are doing. So there is no unified approach. And now these data providers start to save data with cross section. You can find some, but still it's kind of missing point. So if you go to Chinese or American, they are using ADAS, for instance, and these databases, but usually it's quite, for molecules, it's much more difficult. So if you go to, let's say, a more general approach for molecular data, there is no unified approach. So IRENE people is collecting this data, less Aero people, because Aero does not really treat molecules as much, except neutral or ionized particles. But when you come to molecules, if you need, there is a kind of nightmare, because complexity compared to atomic physics is increasing by order of magnitude. Yeah. So simple question, there is no unified, unfortunately.
But thank you for the longer one as well. Thank you very much.
So may I ask you one question, the similar what I asked Samuel. The question is, so as I understand now, for the Monte Carlo approach method, IRENE is calculating the mean free pass. So does it mean that it just keeps for each particle, that's a marker, so it's accounting how much it traveled, that it switches on? Okay, so
it just calculates the mean free path. Basically, it samples from the distribution some distance, and it calculates where the position will be, and that's where the particle will be.
And then it keeps this additional variable is allocated to given marker. So it's counter for each marker.
Yes.
So, I mean, okay, you have a collision, let's say, and then this counter starts to count. Okay, it weighed 1 millimeter, 2 millimeter. It should count. If it should collide in 1 meter, so it really keeps this adding this distance.
I'm not sure what you mean. It's
suppose you say, okay, we have a marker, and you know that marker collided now. So now you calculate what is the mean free pass for this marker. So let's say it's 1 meter. Does it mean that you just, if it's, let's say, time-dependent case, for instance, yeah? So this marker during each time step does not move your whole distance, or it's moving. So so if it's moving less distance than collision mean free pass, what's happening?
I think even in the time-dependent case, it doesn't really matter, because it's just one other dimension, but it's just we know the direction of the particle and we know the distance, so we just calculate where the position will be of the particle after it travels the distance, yeah. And that's it. It doesn't calculate anything between the positions.
Okay, you simply wait until this time happens after. So how you because if you calculate distance, so from here to here,
yes,
so what's happening? Do you calculate time when it reaches this?
No, no time. There's no time basically in this.
So it means that it just next time step you assume that there is a collision here.
Yes.
But if it's time dependent, then it's time longer than your.
Well, if it's a time dependent case, then you can think of the time steps as basically another type of cell. So you just, with the different estimators, you calculate the path traveled through the cell analytically, basically, and that's it.
Okay, so that it means you collide after some time.
Yeah.
This one. Okay, thank you very much. Thank you. So. And now we have Aleš Podolnik. He is a specialist of the PIC modeling. He is one of the co-authors and one of the main simulators of SPICE 2 and SPICE 3 codes. These are 2D and 3D codes used for plasma sheath modeling. So Aleš, the floor is yours.
Thank you, David. Let me just download the current version of my presentation, and I'll start presenting just shortly. So presentation is here. I suppose we are sharing now, so I'll just go ahead. Well, my talk is about other particle.
I think we first.
Okay.
Oh,
Yeah.
now, can you restart, please? Now.
Okay. Good.
Yeah.
My talk will be about the other particle in cell code that we are currently using in large amount of CPU time. It's called SPICE. The PIC part is obvious, and the S is sheath. So it's about basically simulating just a small space between the plasma bulk and the surface itself. I'll be talking about how does the model work and what are the specific features of the model, as well as some interesting results that we have achieved lately. So let me just hide some stuff and use the pointer. Then, first, what we are actually simulating. You have seen a cross-section of the tokamak already several times this week. So again, just a sketch. There is a plasma volume, and there are some interesting regions around, like the plasma-facing components here, or some diagnostics that are inserted into plasma. You can see it like how does it look like in the real device when it was brand new. This is a probe array that was installed in the compass tokamak. That's the brand new part. The tokamak is always older, and there are many tiles of the diverter and limiter. What you can see is one of the interesting parts here are the gaps between the tiles, which in many devices which are present in any device, and they are usually smaller than this millimeter wide gap. And that's the interesting part that was behind the creation of the code, because initially it was aimed to study the interaction between their entering and entrance in the gap. So how does it look like in the model? Basically, you can, if you look here on the one plasma facing components and just turn 90 degrees, you have some objects that are the plasma facing components. There is a small region of plasma in front of that, and we inject some particles or the plasma particles from the bulk to this region. Contrary to David's model, this is a 2D model, and it's much more simpler with respect of to processes that are simulated there. Basically, what we have here are the ions and electrons that are in self-consistent electric field and so superimposed with the arbitrarily directed magnetic field. Yeah, you can see how well some characteristic dimensions here. Usually this this sheath thickness is defined by the physics itself, like one would expect the sheath would be thick. The dimensions in the other directions are usually defined by what we are actually simulating. For example, these gaps are usually millimeter wide, or so the accounting for some shadowing effects with shallow magnetic angle, we get several Larmor radii on one direction and a few of them in the other one. Additionally, what is simulated are some volumetric processes and some surface processes. Volumetric process contains some collisions, which are usually turned off because we started with the collisionless sheath, and just recently we are updating it to work properly with collisions, or surface processes that are mostly secondary electron emissions. I will be talking about it later. So basically, to add some extra information, what we have in the code are, well, some particles that are on a mesh, which is defined basically by the bi-length wide cells. This simulation box is decomposed by domains for each processor. We are using only MPI so far because, well, there is some legacy to the code, and we have some obstacles to overcome so far. Basically, we have periodic boundary conditions along the y-axis and some sources and sinks in the z-axis. Sources are basically the plasma bulk itself, and some secondary electrons coming from the surfaces. Yeah, it's nice to see is also how the quantities are inside the models are normalized to actually enable us to simulate, for example, multiple cases at once. Because if we normalize it properly, we get basically some set of simulations on some in some normalized space, so we can compare it to the more well, actually physical conditions than just one simulation. Then, what is interesting also is the typical dimensions. Contrary to David's code, we have much less cells in one dimension. We have typically hundreds of cells in the Z direction, which is the thickness of the sheath, and thousands of cells in the y dimension, which is the dimension defined by the geometry of the problem. And the simulation runs about 1 million or several 100,000 steps, up to 10 million, but it's very these simulations are very well costly. We usually simulate two species of main plasma particles, ions and electrons, and then we have several species at top, like secondary electrons and so on. We can also simulate multiple species at once, but we rarely do it because, well, we just didn't do it yet. We have about 50 particles per cell per species, so counting with typical dimensions, we have several million particles, up to several tens of millions particles. Learn time is, well, moderate. Most of the cases are done within weeks, but the large and interesting cases took several months to complete, which is partly due to, let's say, well, not really finalized parallelization. The code itself is written in Fortran, mostly old one, and well, however, contrary to the legacy that we are actually following since the development started in 90s, basically. The successful runs are almost everywhere where we decide to install the code. Now we are trying to compile it on ARM processors, but I don't have any preliminary results for that. We usually end at about 100 processes, so modern computer modern. It's just one node at the modern HPC computers, but we don't need more, so we do singly parallel simulations. The IO is some standard libraries, and as we are only 2 developers active, we do it like on agile matter. So if anyone would be willing to try to use the code, we usually grant them their access on need to know basis. And just to give some credits to my colleagues, I'm just the next one in the line of developers. So there are basically people that were working here and in CA France on development and the usage of the code. So some specialties. Basically, this is an overview of the code workflow. As you have seen in David and Jeremy's presentations, is basically the same. You have some weighting, moving, particle injection, and then some diagnostics. Sorry to the outside audience, we just lost our screen, so I will try to fix it now.
We can still see the slides, so you can go on for now. Okay, for the others, okay.
Yeah, but I did it. I shouldn't. No, maybe this interval was decreased, maybe. Yeah. Me too, yeah. But I mean, it was in 4 hours switching off because it was thinking that you do not do anything. So we are putting just doing something here, just tell that we are doing so.
So we probably got our audio system back. So following, again, this is a basic loop of the PIC model, and I'm just pointing out the parts that I considered interesting for the talk. Basically, that's the setup of the model itself. Then a few words on field solver, and then afterwards on particle injection. So how does the model represent the situation of in the sheath? Basically, we have a set of flag grids that represent all the quantities that are necessary for deciding what to do with the particle if you are weighting back. Basically, what's the most interesting feature of this approach is that you can do basically you can immerse basically any object into the plasma. You can see it on the left-hand side. There are 2 objects, blue, green, and 1 yellow ball, which is just to show that basically anything can be there if you define it properly. Now then, these grids are decomposed, that you have some ghost cells around, and from those quantities you calculate some work variables like orientations and where the edges are, what to do with the boundary conditions, for example. We have these local grids for each processor that can be, for example, modified on the fly. So if we decided to simulate, for example, erosion, which when one of the grid points is eroded and the plasma takes its place, we could do it also, although we did not yet do any productive simulations with that. And all the flags that are related to that are usually can be again modified. So if you have a flag grids like that, you will lose a part of memory, but you don't have any complicated structure of boundary conditions, for example, like you have in finite element method, or if you are familiar with SOLPS, that is usually quite a nightmare to prepare the grid properly. We just don't do that and waste a little bit of memory, and then we can simulate the well, basically any object inside Plasma, well, in 2 dimensions, basically, of course. Then we have some global grids, which are a bit of well, legacy thing, but I will tell you afterwards why we have those. And these are basically only for interchange of information about the field. Since it's surprisingly hard to actually have 2D field solver that is both efficient, fully parallel, and well, easily easily implemented, because so far for our problem size, which is about a few hundred cells of the in the linear dimension, the direct solver that runs on a single thread is still the fastest option. We have been recently implementing in the collaboration with BSC Barcelona. Well, they have implemented a faster parallel direct solver for us, which scales only when the problem size reaches some critical dimensions, which is also really good for us, because so far we are limited by memory if we are accessing this large dimensions, since well, we took all the baggage from the linear solver with us. This is the first place I think that I mentioned that the SPICE2 has a 3D cousin, which is basically the same. Because so I don't mention it specifically. There is a significant difference, and that's the field solver, because in 3D the situation reverses, and the fast field solvers are readily available. And again, with the help of BSC, we got this to work. We have a few experimental solvers, which I will not mention it but you can see how does the field look like if well, if this ragged sphere is inserted into Plasma. Yeah, well, it smooths it out, and we don't actually have to care about the sharp corners, since the zeroth order weighting is taking care of that. And yeah, just to reiterate, that's the reason why we still keep some grids everywhere, since well, in full size, since the direct solver is for many cases the best option so far. So about the particle injections, which is again some a nice part of the code that took quite a while to develop, is well, as you are simulating a Plasma, you have to have something to simulate. Yeah, basically some particles have to get to your simulation box. How do we do that? We have a quite a sophisticated injection routine. Basically, we take the projection to the B field, generate all the 3 components of the velocity. First 2 of them in the plane perpendicular to the field are basically Gaussian. And the interesting one is the parallel one, which we use from distribution functions calculated by the full sheath or full field line codes. Like BIT1, we also have tried to cross implement the functions that David simulated, and well, the compatibility is there. So this is an example of how does these different distribution functions look with the with the parameter which is the temperature ratio of ion to electron temperature. Additional to that, we have possibility to inject the particles in non-uniformly. For example, if you are simulating the strike line plasma, you have different densities in short range of dimensions. So to enable the model to do that, we had introduced the non-uniformities in temperature and density. Again, this is the example of how does it look like. We have here three PFC tiles. This is the simulation box in the pink, and this old flat profile of the injection density is compared to the real one, which actually is in scale of the PFC size or in the simulation box size. Another important part of the particle injections is not the plasma itself, but the effects that the plasma or the surface interaction has. Basically, if you insert any object in the plasma, it first heats up and then it's subjected to flux of ions and electrons. So three things can be caused from that. First is the thermodynamic emission, which basically is the intrinsic effect of heating a metal. If you heat the metal in high enough temperature, it starts emitting electrons, which is a source of current coming from the surface, and this current can affect the plasma itself, and also the current can be somehow mitigated by the plasma. The other option is to have a secondary electron emission. So basically, high energy electrons impact the surface, and this causes the ray emission of some other electrons from it. And similar to that is the electron backscattering. So if there is an elastic reaction, so elastic process that's repelling back the electrons back to the plasma. And there are some constraints to that. For example, to calculate efficiently the thermodynamic emission, we have to account for the so-called Schottky effect, which in relation to the surface electric field modifies the effective work function that is necessary for the emission of the electrons. Also, this emission causes development of the virtual cathode in front of the surface, and then you have to resolve the Z direction very carefully in very small cells. Then coming to the examples. In past, as I told you in the beginning of the talk, actually the motivation behind the creation of this model were plasma gap interactions and the next level steps fusion devices. And since then, we have applied the model on many such cases, or followed up with the probe simulations, in which I usually in which I continue so far. But recently, after the implementation of the advanced surface models of electron emission, we have been able to investigate these effects. I will be showing the presentations now, or the results now. Also, the application of non-uniform sources is one of these recent research interests that we follow, and following that, we try to implement the collisions, which so far slow down the code too much, so we have to work on them more. Here, just to review the results. Basically, if you are we have been able to using the simulations that we have provided to our colleagues in Sweden, derive the expression for the total current escaping from the surface that is now used in the code called Memento to model the current that actually caused the movement of molten tungsten on the PFC files. This can be also described by extension to the Takamura law that actually describes the escaping current under some, let's say, regulated conditions, but in plasma it gets worse. So we have applied this correction on the angle. And almost last slide, if you look, if you remember, I was talking about the non-uniform density source. So we have a place on the tokamak diverter. It's called a strike line for those not familiar, but I don't think that there are none. And this strike line is affected by local electric fields. Basically, if you have different orientation of the magnetic field with respect to the surface, which, well, in one of the strike lines you have those this one and the one this in the opposite direction. There is a heat flux footprint that is generated from by the plasma that is interacting with the surface, and this heat flux footprint moves. And this movement is caused by different electric fields that are caused. This movement is caused by the crossbridge derivative. It is caused by different structure of the electric field in front of the tail. You can see just how this ion streamlines are flowing on the surface in the case of the forward and backward magnetic field. This is a comparison of two different values of the temperature. So if you have large temperature, then you have thick pre-sheet and it's stronger field forms, and the magnitude of shift is different. So what are the current challenges now? We are not sleeping. We are developing more and more features into the code. Currently, we have received the Czech National Science Foundation grant to study a so-called inverse sheath. Basically, if you have a emitting surface, you can reach the state where the potential is defined by the emission, which causes the shift from this classical exponential potential evolution to something well completely opposite. Basically, you get exponential, but from the positive potential to zero, as some preliminary simulations indicate that it could be possible to obtain. And again, we are working on advanced probe physics, and this is my summary to show you some list of the features and some summary of publications. So thank you for your attention, and if you have any questions, just feel free to ask, please.
Thank you. I would have just on this last ones, I would have the one before.
Yeah, this one.
So, as I understand, the SPICE code is still just a sheath code, correct?
Yes.
So have you ever tried implementing any sort of feedback on what your sheath drop is? Because I failed to see how you plan to simulate things like inverse sheath potential.
Yes, in the sheath, in inverse sheath, we are actually implementing the double bounded system to account for some, well, say, simplified scrape of layer model, and to have this resolved properly.
And okay, so on that matter, also about the ball pen probe, what do you plan to do, because you have dielectric inside?
Yes.
Nobody knows how it works, so I don't know how you think you
Yeah.
do it with simulation.
Yes, so we don't know how it works either, and that's the aim of the project, to find out how it works.
Good luck.
I think there is a question from Mikhail, please.
Yeah, wonderful talk. One question I had, which has nothing to do with all the specifics you showed, but I was quite surprised to see that you can go up to 10 million time steps. Was this?
Yes.
Yes. So how do you manage with any numerical shortcomings of the method? Because 10 million is quite impressive.
Basically, we don't simulate one particle for the same for the whole amount of time, and since this particle is consumed by the boundary, then the other one is generated, and it starts again.
Ah, okay. Now I get it. Okay. Thank you very much.
Welcome.
Just shortly to comment what Michael said. Michael, 10 million is a very small number. Usually edge codes, especially sol codes, we use up to 10 to 9 time steps. So.
Ouch. Okay. Thank you very much.
It's different from, this is the main difference between plasma, one of the main difference between plasma laser interaction and edge codes.
Yeah. 10 to the 9 is quite impressive. Thank you.
Hi. So thank you for a very nice talk and introduction to this code. I want to go back to the slide where you sample the incoming distribution function, which satisfies the bump condition.
Yeah,
the Kadura condition, essentially. Can you tell me what the analytical formula for this?
Well, there are no analytical formulas. This is an output of other numerical simulation.
Which code produces this?
That's a good question. I just don't have it in my head now. It's very old code. Maybe David remembers. PIC, I think.
I mean, in this case, it's a PIC. Yep. So it's a. But I mean, we have more advanced cases with BIT1. So.
Yeah, basically, we can take also the output from BIT1 and plug it in.
I mean, PIC is quasi PIC, so that's why it's called PIC. It's faster, much faster, but the number of simplifications is all CA code, so by Jimmy Gunn. But I mean, if simulations are ready, you can take from any PIC simulations.
Yeah, we can also plug in, for example, Maxwellian, which we use for some comparison.
Yeah, but Maxwellian is not gonna.
Yeah, well,
satisfy the Kadura condition.
Yeah, it will not, but you can shift it, for example.
you can actually. Okay, so how does this? So the distribution function, I imagine, will also depend on the collisionality of your upstream, right?
Yes, but basically we take the same one for the all simulations, since we don't have, well, to have it properly resolved, you would have to run a simulation like with one for every input that we have. But so far, for example, if you put just a shifted Maxwellian, you don't have much different results.
Okay.
But this is an, well, since you can see that there is a large tail of fast particles, which slightly differs from Maxwellian for the one the ion temperature equal to the electron one, you get very similar to Maxwell shifted Maxwellian. If I would plot it over there, it would look like almost shifted Maxwellian. But if the ions are very fast or faster than electrons, then you get some different effects. But we usually stay in the safe region.
Okay, thanks. Yeah, the reason why I ask is I also do a sheath code, and I use a Tor distribution function of the form V parallel squared times the Maxwellian.
Yeah,
actually.
I think that's one of the options that could be used.
A Kadura condition, but like it seems a bit different, the distribution function that you used. So, yeah.
Basically, that's time proven, and since we have we don't have many options how to upgrade it, since BIT1 simulations are expensive, then we just use this. What do we have?
I have also one. I don't know if I caught correctly when you were talking about 2D solvers and 3D solvers.
Yes.
And if I understood correctly, you somehow mentioned that 3D solvers are more easily available, or what?
Well, basically, they are as available as the 2D ones, because if you are just solving a matrix, it's okay. But the 3D solver, that's a let's say empirical observation, scales much better than if you are. Well, we are using old multi-grid solution. There was also one threaded library. And if we are comparing the one that we got, it was eventually based again on this direct solver in the, let's say, innermost grid. It was more readily replaceable by 3D approach parallel approach, because basically that's how it is. The matrix is more complicated, and then the parallelization is more efficient on the complicated matrix.
I actually had a question about this, about PEPSC as well. As I actually use that, and my experience is that it does scale, but I'm kind of curious, when you say 500 to 100 cells, is that per processor, per rank?
No, it's one linear dimension. So we actually have 500 times 500 and that's it for the whole dimension of the cell. And the PEPSC for our usage reaches its limits about 2,000 cells by 2,000 cells. If it's
in parallel or not?
No, it's not in parallel.
Oh, I think there is a parallel version.
Yes.
Yeah, I think so.
Oh, that's a good thing to hear, because we are somehow stuck with the old one.
Okay, all right. Yeah.
Thank you.
Okay, so thanks. Let's thank Sar once more, Aleš. And now we come to the presentation from Kalia. She will discuss the vectorization of BIT1. So Ale is supporting us in optimization of BIT1 code. She's a member of Plasma-PEPSC project. Please, Kalia, floor is yours.
Yes. Hello. I hope you can hear me.
Yes, please go ahead.
So I'm Kalia Chronaki, I'm from Fourth, and today I'm going to present to talk about vectorizing BIT1 kernel. So we're going back to BIT1 now for long vector architectures. Sorry. Okay, so this is the overview of the presentation. First, I will give a bit of context regarding the Plasma-PEPSC project, where this work is based on. Then I will give some information about the hardware that we use. After, I will explain about what is vectorization and how it is performed. Then more specifically, how we do the BIT1 vectorization. And finally, I will present the experimental results. So the Plasma, this is a project that revisits a set of particle-in-cell codes, including BIT1, and this is in order to optimize them and use them in various different architectures. Other plasma codes that are studied in Plasma project are PIC GPU, Glaciator, Gene, and GeneX. And more specifically, this work is located in the work package 2 of Plasma project, where we focus on optimizing the above particle-in-cell codes for vector architectures. One architecture is the EPI processor, RIA processor, which, and this task is being implemented by Cypern. And the other is the EPI accelerator, or EPAC RISC-V accelerator. And this task is in collaboration between BSc and Fourth, and what I'm going to present today focuses on this hardware, the API accelerator. So as I said, yes, this is our hardware, the APAC 1.5, and this is a joint effort. It has many components, and each component is implemented by a different party, and one of the partners is Forth. Where we focus is the red circled area, which is the core, the RISC-V core that the APAC chip has, which is a general purpose RISC-V core, and the vector unit, which is the unit that executes the vector instructions, and that's why we do the vectorization of the codes in order to take advantage of this unit. So the RISC-V core is the model named Avispado. It is implemented by a company, Semidynamics, and it implements the RISC-V instruction set architecture. And then the RISC-V vector implements the RISC-V vector extension. This is implemented by BSC. And this vector unit executes instructions that are applied. One instruction is applied on multiple data. So when we execute one vector addition, this addition means that we have 4 additions, for example, depending on what we set. As is shown here, one vector unit instruction corresponds to multiple similar instructions operated on several elements of the vector register. So this diagram here shows a scalar register instruction, how it is performed. So A0 plus B0. This is the simple case for a general purpose core. And then when we have a vector register instruction where we add 2 vector registers, each register can store multiple elements. So one register contains the values A0, A2, and A3, and the other register contains the values B0, B1, B2, and B3. And when we perform one vector addition of these 2 registers, we simultaneously perform these 4 additions that are shown in this diagram. Now, the key features of this accelerator architecture, even compared to other vector architectures, is first that it uses very long vector registers. So the vector register of the APAC 1.5 holds up to 256 floating point elements, 64-bit, 56 doubles, up to 256 doubles. For comparison, a scalar register, which is not vector, is 32 or 64-bit, depending on the system. And now other vector architectures have the vector register sizes that appear in this figure, where you can see for comparison, the last line is the size of the APAC vec that we're talking about. So it is 16K bits per register. Also, this architecture is vector length agnostic. So what this means is that it can support multiple sizes of the vector length, and this can be set at runtime. In the figures below, you can see that, so the first describes the registers of a scalar processor. So it's 64 bits per register. The second, the one in the middle, shows what can be done in other vector architectures that are not vector length agnostic. So a non-vector length agnostic vector architecture can support either to use the entire register. So for example, 4 elements at once, or not use, or use just one. So not use vector register at all, use scalar register. In our case, we can tell to the system that now I want to use only 2 elements of the vector register, for example, or now I want to use 4 elements of the vector register. We can set it at runtime in the program. Now, what we can do, how we can vectorize our code for the EPAC 1.5. There are some development options for this hardware, because we need to write code differently, use a different compiler, because we need to generate a binary appropriate to execute vector instructions. So there is a compiler implemented based on LLVM that generates binary for the EPAC 1.5. And this compiler supports either auto-vectorization, or we can also use manual vectorization with this compiler. The first option, which is the auto-vectorization, this signifies that we provide a flag in the compilation line, and we also add pragmas in the code to give hint to the compiler what are the areas that the compiler needs to vectorize. In this table, I have added a small snippet, so a very small loop. And then next to it, it's the code with pragma. So when we add this pragma, if there are no dependencies in the code, then the compiler generates vector instructions. So the pragma clang loop vectorize enable. This is one way of generating vector instructions, but many times the code is not written in such a way where there are no dependencies and stuff. So sometimes we need to perform some manual vectorization as well. So the second option is the manual vectorization. And to do this, we can use intrinsics, which are, we need to rewrite the code using the intrinsics, which are built-in commands that the compiler directly translates to the corresponding assembly instructions. And these assembly instructions are vector instructions. And then the last resort is using directly assembly through the ASM library, where we need to rewrite the code with that, but this is very error prone, difficult for the programmer, so it's not generally recommended to just go and write your assembly. Now I will show an example of a very simple example of how we can do manual vectorization using intrinsics. And these are 5 steps. So this example might not be the optimal one, but I wanted to add these built-in commands to show you a bit what they do. So the first step in any case, not only in this example, is to set the vector length. So this is the GVL, the granted vector length. To set the vector length, we use this built-in that is shown in the first line, which is the vset VL max. And this returns what is the maximum vector length that we can get from the system. So this number is then the number of elements where each vector instruction is going to be performed. So if the GVL is 4, when we perform a vector add, we will perform 4 additions on 4 pairs of elements. Then the second step is to load data from memory to a vector register. In order to initialize a vector register, we need to use a built-in command. So here we have a API vload command, and this initializes the xvec. I don't know if you can see my mouse. Maybe I can point here. It initializes the xvec, which is a vector register, with the contents in memory at position X. And it initializes GVL elements. So GVL number of elements go in xvec starting from position X in memory. This is one way of initializing a vector register. And then in step 3, I'm showing another way to initialize a vector register, constant value. So one vec is another vector register. And here with the vbroadcast command, I initialize it to 1. So if GVL is 4, then this one vec will contain 4 ones. So 1, 1, 1, 1. Then step number 4 is to perform the operation, which is equivalent to this for loop. So if we want to add, so xi equals xi plus 1. This is very simple. And we perform this for GVL elements. So to achieve this, this can be achieved in one line for the vector case, and it is with a VFAD, the 2 registers that we just initialized for size GVL number of elements. And finally, the 5th step and the final one is to store the result back to memory in X. So this does the opposite to vload, so it goes the other way. Now we take the contents of the vector register, the xvec, and we store it back in memory starting at position X for GVL elements. And now this example can be also visualized here as source code, pseudocode maybe, because I have this random value array which is not correct, but yeah, it's pseudocode. So if we say that X has 512 floats, and we want to increase all of them by 1, then by adding these built-in commands in this way, we can have the vectorized execution. More information about the intrinsics can be found here. There are many built-in commands like these, and this is mainly what we used in the manual vectorization of BIT1. So now I will move a bit to combine our work with what I have explained so far. First is a short BIT1 investigation that we have done. So this is a diagram from my understanding for the BIT1 code. I'm not an expert of BIT1. So the BIT1 has these stages. First is an initialization part, and then there is an iterative stage that includes these steps that are written here. So the particle mover, the arranger and wall interaction, collisions, density calculator, and field solver. The first thing that we did when we started working on BIT1 was to identify the hotspots in the code. To do this, we used Macao, which is a profiling tool, on an x86 platform, and we executed the whole BIT1 code to see what functions and loops are the most time-consuming in BIT1. This table shows these hotspots in starting for the most time-consuming one. This is similar to what Jeremy presented. It's basically a reproduction of the results. So the most time-consuming function was the arranger. Then was the AVQ. And after that, we found the mover functions, move 0 and then move, which combined are around 30% of the execution time. Now, when we tried to apply automatic vectorization to these hotspots in BIT1, we saw that the compiler was not able to automatically vectorize most of these areas, but it was able to automatically vectorize the mover functions, because the loops in the mover functions are more vectorization friendly. So we decided to start with these functions, the mover kernels, and we followed this methodology, which we still follow, in order to work with vectorization and with the multiple functions of BIT1. So first, we extracted the kernels from the BIT1 one by one, and we are able to run them in isolation. Then we do auto-vectorization of the kernels in isolation and evaluation on the PIC 1.5. And finally, we do manual vectorization again on the kernel in isolation. So the first kernels that we have extracted are all the mover kernels. Now, after the automatic vectorization that we applied on move 0 and then move, we gathered the execution time results on the PIC 1.5. So here we have applied our pragmas, and we have used the compiler asking him for auto-vectorization. And on the charts on the top, we can see the execution time on the y-axis and the number of iterations on the x-axis, which is the NP in BIT1, the number of particles. So we can see that after NP, when NP increases more than 60, the auto-vectorized version is faster than the scalar version. So, sorry, on the top charts, the lower is better. Here is the speed up, so here higher is better. Here is the speed up over the scalar version. So yeah, once we reach 60 iterations, we start to observe improvement of the auto-vectorized version. And our improvement reaches up to 8 times faster execution for 500 iterations. This is with the automatic vectorization. And now let's move to see with manual vectorization what we can achieve in terms of performance. So we implemented this manual vectorization. This is a very small part of the code of MoveB. Just these lines are translated to this for the vectorized code. And here I have marked with red all the vector setup instructions, let's say. As I described earlier, these contain the set of the vector length, broadcast, so initialization of vector registers, load from memory, these types. The rest of the instructions are pure computational instructions. So subtraction, multiplication, addition, and stuff like that. So here you can see that it's interesting to note that we have an extra set of all the instructions once again after the loop finishes, and this is in case the number of iterations is not a multiple of GVL. So if GVL, if there is a remaining number of iterations that has to be executed, we can always recalculate the vector length. And this is why the vector length agnostic feature is very important, because at runtime, we can choose a different vector length and perform our instructions with this new granted vector length. So now I will show the evaluation of the manual vectorization. Here I have just 3 of the kernels, and move1 and MoveB. This is execution time, so the lower is better. Blue lines are the scalar code, and orange lines are the vectorized code. These codes run in isolation, so it's not the entire BIT1, it's only the kernels. So we can see that the vectorized version is able to maintain the execution time at a low level because it significantly limits the number of iterations since it performs each instruction on multiple data. And now here is a chart that contains all the mover kernels, and it's the speed up of the vector version of each kernel over the scalar version of each kernel. Now here it is interesting to observe that move0 and then move, they reach up to 18 times faster execution when we compute 500 iterations of the code. These are the kernels that have the fewer computations inside each iteration, so the loops are simpler. Then it's move1 and MoveB0. They reach up to 14 times speed up, a bit lower than move0 and then move. These have a bit more computations, a bit more complexity inside the loop. And finally is MoveB, which reaches up to 10 times faster execution. And this is the kernel that has the most complex computations. We attribute this to the reuse of the vector registers, because the vector registers are limited. We don't have an infinite number of vector registers. So when there are many computations, we need more registers, and then the execution has to stall in order to reuse a previously used vector register. So this creates a delay and limits a bit the performance. So now for the next steps, we can't wait to get performance results of the entire BIT1 application once with the applied vectorization of the kernels. The thing is that we don't have the hardware is not ready yet. So the hardware team is working on a 2-node EPAC chip setup so that we can run MPI there, because so far we use only 1 node. So it's 1 core and 1 vector unit for now. Then we might try some further optimizations of mover, like inline assembly, but we are more focused on continuing the vectorization of the next hotspots of BIT1, so that we can have maybe a fully BIT1 vectorized version. And that was all from me. Thank you for your attention. And I would like to thank my colleagues as well and the partners that we have collaborated and have helped in this work. So if you have any questions, feel free.
First of all, thank you very much, Kalia. I mean, I have a question, but maybe someone else. Okay, so let me ask the following question. I mean, these are very good developments. The question is, how transportable is this? How universal is this vectorization approach? So suppose we vectorize and we use BIT1 with your accelerator, and then I take this code, for instance, with vectorized version and put, let's say, in Carolina or Vega or Leonardo or other machines. So what will be output?
Yes,
we needed
so
to load libraries, corresponding libraries, or
so the machine that this code is able to run has to implement the RISC-V instruction set architecture, and it's the vector, also the vector extension of the RISC-V. So it's a different architecture. It's like we say ARM or x86. So for Carolina, I'm not sure. It must be x86, correct?
yeah, but I mean, suppose there's a user, let's say not advanced user, he takes the code and wants to run it. And suppose this machine does not have this, let's say, accelerator. So what will happen? Will code will crash, or will just use, let's say, without a vectorization?
So right now, our implementation is just in isolation. We can implement a mechanism within BIT1 that ignores the version in case there is no hardware support. So right now, the state of the code is that it won't run. It will throw an illegal instruction. But when we port all of these changes in BIT1, then there are some mechanisms that you can check what hardware am I running on, then use this version of the function. Otherwise, use the other version of the function.
Oh, excellent. So this can be done, yeah? So
it can be done, yes. We can have this version within BIT1 just in case someone runs BIT1 on a platform like this.
Okay, oh, this will be brilliant, because I mean, every user don't want to dig in the exact architecture of given machine. So, but if code will have option that capability to, let's say, identify and choose the proper version of the, let's say, vectorized or unvectorized version of the, routines, it will be brilliant. Yeah.
Yes, this can even be set in the make file, for example, or yeah, have different files, or yeah, there are many ways.
Yeah, I mean, we will come to this point. Let's finish.
Yes.
Okay, thank you. Any other question?
Yeah, one from my side, David.
Yes, please.
So thank you very much for the overview. You mentioned briefly the number of limited registers, which is very similar if you have groups of threads running on a GPU. And there are many ways to reduce the amount of used registers. For example, you can bring down the floating point precision, or you can make certain parts of the code and put it into smaller, more versatile parts with limited register use. Do you do any of these changes to the code as well, or do you take basically the different parts of the code just as a package as is and try to vectorize them and see their performance, or do you actually try to reduce register usage as well?
Yes, we are constantly in contact with David when we start a kernel, and there are cases that we have changed. We have switched to single precision for some variables. Now we need to investigate more if actually this helped. But it's always better to switch to single precision whenever possible for performance reasons. But yes, we try to perform optimizations, and when there is something that is worth asking David if we can change, we do. And then we can see how this can be applied in the entire application.
Okay, thank you. And maybe a follow-up to this, since you already mentioned that you're in constant contact with David. If you have a special optimized version for a certain hardware and you're developing this together with the code owners, it is usually very helpful to have at least one of the code owner developers to be deeply involved in that, so that long-term maintenance is assured. How do you do that? Can you explain a bit the process? Because at some point the code owners will have to take over that optimized version and will have to maintain it, or it's probably dead at one point. So how do you do that?
So Michael, what we do is we basically have our version where we have extracted the kernels that we are working on. So we have a repository where we have these kernels that we're working on, but they are only the functions. These are only the functions. It's not the entire BIT1. Then what I'm doing is locally, I can take this version of the kernel and put it in the BIT1 project. Yes, put it in the BIT1 project and then run it entirely. Now, maybe I could provide to the code owners the BIT1 project that I will end up with after having all these vectorized kernels, but we will need to, when we reach this point, I think we will need to have some meetings and collaborate more to see how we're going to add the different versions of the code, as David asked also earlier, because yeah, the code needs to be portable. We cannot have only the vectorized versions. So yeah, we have not reached this point yet, actually.
This is a very heavy question, and heavy to
But
answer
we have
question.
to, yes, we have to get involved when more involved with the code owners when we reach that stage, I suppose.
Thank you very much for that answer. Thanks a lot.
No problem.
Absolutely agree with Kalia. At the end of project, we have to merge quite number of branches, and this is nearly getting really serious problem, because we have one advanced CPU version, then with more atomic physics and with let's say loading, so uniform loading. Then we have one version with GPU and with I/O, so advanced I/O. We'll have version with vectorization. So, and I today asked question how to, just merge this, and it seems that it's quite heavy work at the end of the project. So, but we have to do it. I think if the direct, from my point of view, I add to what Kali answered, the main point will be to, when we finish work, we have to have very well described manual. If you have a well-described manual explaining what was done, just very shortly, but exactly on topic. So these are the functions we used, and this has to be done. This is applicable to these architecture machines, and this is how it's choosing which version of the vectorized or unvectorized. And I think this will be good basics that if one needs further uploads, we can follow this description. And to my understanding, and I all time saying that well updated code is not just only code, but it means also well described manual, what was done and what are the functions there. Unfortunately, BIT1 is not the code which is well described, but I was told by Eurofusion responsible people that this is one of the best well-described code in this community. So this is not very good to know, but this is a necessary step. So I think this is one of the ways to reduce probability that codes will be, let's say, not supported in future. So.
Okay, thank you very much, David.
Yeah, so we thank Kalia once more. Thank you very much, and thank you very much for your support.
Thank you.
Now we have a coffee break, and we come back in half an hour, so 25 past 4. And please don't be surprised. Maybe I will be disconnect because I want to save recordings, and sometimes it needs to be closing the Zoom meeting. So just, I don't know if I'm hosted. If I now try to generate movies, it might require closing. So please don't be surprised. I will reconnect it half an hour. Thank you. Set up some case from